Kepler-452b was once placed very close to the dream humanity has always been searching for, another world that could resemble Earth. It orbits a star fairly similar to the Sun. A year there lasts about 385 days, and its orbit lies within a region where liquid water has not yet been ruled out as a possibility if the atmosphere is suitable enough. But that very uncertainty is where all of that hope begins to tremble. If Kepler-452b is truly a rocky planet, and if current mass estimates are not too far off, its surface could lie beneath a gravitational field far more severe than the one on our world. An atmosphere thick enough could help retain water and heat, but it could also push this planet toward a Venus-like greenhouse effect. From a distance of nearly 1,800 light-years, Kepler-452b still looks similar enough to make humanity hope. But the closer we look, the colder the question becomes. Is this truly a world that could nurture life, or only the appearance of Earth created by a distance too vast to see clearly? The allure of Kepler-452b did not begin with a clear image. It began with a very small change in the light of a distant star. No one has ever seen the ground of this planet, if that place truly has solid ground. Its shores, clouds, horizon, and colors have never been recorded directly. What brought Kepler-452b into the story of life beyond Earth was only a single dimming of light. When this planet passes in front of its parent star, the star's brightness drops for a short period of time. From that faint sign, astronomers began reconstructing the size, orbit, and position of a world located nearly 1,800 light-years away from us. A world that does not appear through an image, but through a very small absence of light. What makes Kepler-452b different from many other exoplanet candidates is not found first in the planet itself, but in the source of light it orbits. Kepler-452 is not a small, dim, and flare-prone red dwarf, the kind of star that often appears in discussions about potentially habitable planets. It is a main sequence star with many traits closer to the Sun. In the search for life, the parent star is not a minor detail. A planet may lie at the right distance, but if its star is constantly releasing powerful bursts of radiation, that planet's atmosphere would have to endure them for a very long time. That does not make Kepler-452b a safe place. But this world begins from a context that more easily draws human attention. It orbits a source of light more familiar from the only environment we know has ever allowed life to appear. Not because Kepler-452 is a perfect copy of the Sun, but because this star system suggests a setting less alien than many planets orbiting tightly around smaller and more violent stars. The orbit of Kepler-452b makes that association even stronger. This planet takes about 385 days to complete one orbit around its parent star. That number is close to the rhythm of an Earth year, and that very closeness makes the imagination open up easily. A distant planet orbiting a star fairly similar to the Sun, with a year not too different from our own. But in science, an Earth-like orbit only opens the first door. It does not tell us whether oceans exist there. It does not tell us how thick the atmosphere is, nor does it prove that the planet's climate has remained stable long enough for complex chemistry to have time to develop. The reason Kepler-452b is mentioned so often lies in its position within the habitable zone. There, the energy from the parent star could allow liquid water to exist on the surface if the planet has a suitable atmosphere. The word "if" has to remain. The habitable zone is not a promise that life will appear. It only says that the planet has not been ruled out of the search from the very first step. The rest depends on things much harder to measure, from atmospheric composition, surface pressure, initial water content, geological activity, magnetic field, to a climate history stretching across billions of years. That is why Kepler-452b is not compelling, because it has answered the question of whether humanity is alone. This planet is compelling because it places that silence inside a setting very close to what we hope to find. Not an icy world orbiting a faint star. Not a planet heated too intensely by being too close to its parent star, but an object larger than Earth orbiting a relatively familiar star in a place where liquid water still has not been ruled out as a possibility. But from here, caution must begin. What humanity knows about Kepler-452b still comes primarily from indirect signals. That world could be a rocky planet. It could also be far more different from Earth than the feeling created by the first numbers suggests. The distance to Kepler-452b forces every answer to pass through models, probabilities, and assumptions. The true value of this planet does not lie in the name Second Earth. It lies in the gap that name opens. Kepler-452b is similar enough to make humanity hope, but still too distant and too lacking in data for that hope to become a conclusion. When a planet is called Earth-like, human imagination often moves faster than the data. That phrase suggests oceans, clouds, rock, sky, and somewhere that could be stood upon. But in astronomy, similarity often begins with very limited parameters. A planet may have a size close to Earth, receive an amount of light not too different from Earth, or lie within the habitable zone around its parent star. Those things are worth noticing, but they are not enough to turn a distant world into a place that is truly habitable. Earth comparison indicators should only be seen as the first filtering step. They help scientists arrange thousands of exoplanets in a more orderly way. A world with a high level of similarity may be worth observing further, but life does not begin from a score. It depends on the entire history of that planet. Whether water exists or not. What form that water takes. How long the atmosphere can remain. Whether the surface is constantly altered by radiation. And whether the climate remains stable long enough for complex chemistry to have time to accumulate. The solar system itself shows that this problem is harder than it first seems. Mars once had liquid water on its surface. Dry valleys, ancient riverbeds, and water-related minerals all show that the red planet was not always as cold and dry as it is today. But Mars is too small to hold onto a thick atmosphere for a long time. As that layer of gas thinned, surface water gradually lost the ability to remain stable. A world that once showed many promising signs can slide into a cold, dry, and almost silent state. Venus is the warning on the other side of the same problem. This planet is closer to Earth in size than Mars. It is a rocky world with an atmosphere. But that atmosphere is too thick, too rich in greenhouse gases, and traps heat so intensely that the surface has been pushed into an extreme state. If we only look at size, Venus seems close to Earth. But when we look at its actual climate, it shows how far a rocky planet can move away from habitability. Mars and Venus place Kepler-452b in its proper position. This planet cannot be judged only by the fact that it lies within the habitable zone. That zone only says that liquid water has not been ruled out from the very first step. It does not tell us whether water truly exists on the surface, nor does it tell us whether the atmosphere is protecting the planet or silently turning that world into a heat trap. It says even less about whether the surface has remained stable enough for billions of years for life, if it ever began, to make it past its earliest steps. With Kepler-452b, the hardest part lies in the things that cannot yet be seen directly. Humanity knows that this planet orbits a star relatively similar to the Sun. Its orbital period is close to an Earth year. Its size is larger than our world. But the most decisive factors still remain beyond direct measurement. What the atmosphere is made of, what the pressure is like at the ground, whether there are oceans, whether there is a magnetic field strong enough, whether the interior is still geologically active or cooled long ago. Those details are what separate a planet that only appears promising from a place that could truly sustain a living environment. This is the trap of the phrase second Earth. It makes a distant world feel closer in the imagination, but it can also make humanity overlook the most important differences. Earth is not habitable simply because it lies at the right distance from the Sun. Our planet is habitable because many conditions have coexisted for a very long time. An atmosphere that is neither too thin nor too thick. Liquid water on the surface, a climate that was not pushed into extremes too early. A geological history active enough to recycle material, and an environment stable enough for life not only to appear, but to have time to change the very planet that gave rise to it. So Kepler-452b does not become less interesting when viewed with caution. On the contrary, this planet becomes more remarkable. It forces humanity to go deeper than the Earth-like label. A planet does not need to be a copy of our world to become important. But if it is viewed as a candidate for life, each layer of conditions must be examined more carefully. Kepler-452b does not only raise the dream of another Earth, it raises a much harder problem. How many fragile conditions must a world preserve before hope for life truly has a foundation? Kepler-452b is not the only candidate that has ever made humanity think of a place that could be habitable. In the list of exoplanets that have been discovered, there are worlds closer to Earth, smaller, easier to observe, or receiving an amount of energy from their parent star that seems suitable. But the closer we look at each case, the more one truth becomes clear. No planet only needs one correct condition to be enough. GJ1002b is one example. This planet lies far closer to us than Kepler-452b and orbits a star smaller and dimmer than the Sun. That proximity makes this star system an attractive target for future observations. But that advantage comes with another limit. Because the parent star is dimmer, the zone that receives enough heat has to lie much closer to the star. An orbit that close could place the planet in the problem of tidal locking, where one half of the world always faces the source of light, while the other half sinks into long-term darkness. In that scenario, liquid water does not depend only on distance from the parent star. The decisive factor lies in the atmosphere's ability to transport heat. If the layer of gas is thick enough and stable enough, the boundary region between day and night may become less extreme. If not, one side could be heated continuously, while the other side becomes so cold that water is locked tightly in ice. A planet that appears to be in the right position to hold water could still be split in two by its own orbit. GJ 1002c pushes the problem in another direction. This planet lies farther from its parent star and may be colder. For a world like that, the surface may not necessarily be the most interesting place. If water exists, it could be hidden beneath ice or appear only in environments warmed from within. It could be concealed beneath a cold crust in darkness, where heat and minerals from rock are still enough to keep chemistry going. K272e points to another risk. This planet also orbits a small star cooler than the Sun. A world like that may receive a suitable amount of energy, but this type of parent star often forces scientists to pay attention to radiation activity. Powerful flares, if they occur long enough and often enough, could erode the atmosphere, alter surface chemistry, or force hypothetical life to shelter underwater, underground, or behind a protective layer thick enough to survive. That does not remove red dwarf systems from the search. It only makes the problem harder. A planet may be at the right distance, but still have to exist beneath a star that is not entirely quiet. These cases do not pull the story away from Kepler-452b. They help clarify why Kepler-452b once drew so much attention. Compared with many worlds orbiting close to small and unstable stars, this planet moves around a star that seems more familiar to the only experience humanity has with life. Kepler-452b is not immediately drawn into the problem of one half in day and one half in night, as many planets close to red dwarfs are. Its most prominent risk also does not begin with an overly violent parent star, but that advantage does not turn Kepler-452b into a copy of Earth. It only shifts the focus of the story to another place. For this planet, the problem no longer lies mainly in whether that world is tidally locked or not. The problem lies in the body of Kepler-452b itself. This planet is larger than Earth. Its true mass still depends on estimates, but if it is a much heavier, rocky world, gravity would no longer be a minor detail in the observational profile. It would become the quiet underlying force that determines terrain, atmospheric thickness, pressure on the ground, and even the limits of a hypothetical biosphere if life ever had a chance to begin. When the story returns to Kepler-452b, what stands out is no longer only its orbit or its distance from its parent star. Those data points place this planet on the list of candidates worth observing. But the harder part lies in the body of that world itself. If Kepler-452b is truly a rocky planet, and if current mass estimates are not too far off, surface gravity could become one of the most important factors in the entire story. Gravity does not need to appear in an image to decide what that image looks like. It pulls matter downward, presses terrain into a more stable state, limits the height of mountains, the steepness of rocky slopes, and the way sediment settles after each disturbance. A landscape under a stronger pull would not only be shaped by volcanoes, impacts, or erosion, it would also be rewritten, little by little, by a pressure that is always present, silent, and unrelenting. If Kepler-452b has a solid surface, every layer of rock and every mass of material on it exists under a greater load. The terrain cannot be imagined as an enlarged version of Earth. Mountains are not simply mountains. Plains are not simply plains. Every height has to pay for itself through the stability of the material beneath it. Every steep cliff has to resist a pull that is always trying to drag it down. Even a region that appears quiet could be the result of a long balance between rock, internal heat, and gravity. On a world like that, the first sensation, if someone could stand on the ground, would not come from the sky or the horizon. It would come from the weight of the body itself. Every step would require more strength. Muscles would have to work harder. Bones would carry a greater load. The heart would have to push blood under harsher conditions. Standing still, bending down, lifting a small object, or crossing uneven ground could all become energy-consuming actions. This is only a way of imagining it, not something that has been observed. But it shows that gravity is not a minor number in Kepler-452b's profile. It is something that could turn the entire experience on the surface into a different reality. Gravity also interferes with the layer of gas around the planet. A world with greater mass usually has a stronger ability to hold on to gas. That could help maintain a stable covering for a long time, but it also opens another problem. When the atmosphere is held more tightly, pressure near the ground can become a decisive factor. Air would no longer be only something to breathe. It would be part of the physical environment, pressing down on the surface, affecting heat, water, weather, and every chemical process that could occur there. So the gravity of Kepler-452b is not only about how much a person would weigh if they set foot on that world. It is a governing force from the rock below to the gas above. It affects how rock cracks, how mountains form, how water flows, how the atmosphere is retained, and how a hypothetical living environment would have to adapt if it ever existed. Even water, if it exists on the surface, would not escape that influence. Waves, currents, sediment, coastlines, and seafloors would all operate within the same field of force. A hypothetical ocean on Kepler-452b would not only be a place that holds water, it would be an environment shaped by pressure, heat, chemistry, and gravity at the same time. Within it, every process, from erosion to the water cycle, could be far different from the familiar image on Earth. That is why Kepler-452b cannot be treated as a familiar place simply because its orbit suggests hope. If this planet has ground, that ground lies under its own distinct pull. If it has an atmosphere, that layer of gas is held under its own distinct conditions. If it has water, that water flows, settles, and evaporates in its own distinct environment. Before asking whether Kepler-452b could nurture life, we need to ask something more basic. Whether that world can allow a stable environment to exist under the weight of itself. After gravity, the next major problem for Kepler-452b lies in what surrounds the entire planet. A rocky surface is not enough to create a living environment. Light from the parent star is not enough either. Between the ground and space, there needs to be an intermediate layer strong enough to retain heat, regulate climate, and create pressure for chemistry to occur steadily. But an atmosphere is not just a veil surrounding a planet. It is the system that determines how energy enters, stays, and then escapes. When light from the parent star reaches the surface, part of that energy is absorbed and warms rock, water, or clouds if they exist. That heat then has to be radiated back into space. If the gas composition is suitable, this process can help stabilize the climate. If too much heat is trapped, the surface can be pushed into a state that becomes increasingly difficult to reverse. For Kepler-452b, the notable detail is that this planet receives more energy from its parent star than Earth does. That number does not automatically turn it into a place that is too hot, but it makes the role of the atmosphere more sensitive. An atmosphere that is too thin could make it difficult for water to exist over the long term. A thicker atmosphere could help retain water, but if it traps heat too strongly, the boundary between stability and loss of control would become very narrow. Water, if it exists on the surface, would take part directly in this feedback loop. As heat rises, more water evaporates. Water vapor itself is a powerful heat-trapping gas. The more water vapor there is in the air, the harder it becomes for the planet to release heat into space. When more heat is retained, evaporation continues to increase. A loop like that could turn an ocean from the foundation of hope into part of the very mechanism that makes the planet heat up. The hardest part is that there is currently no clear answer about Kepler-452b's atmosphere. From transit data, astronomers can infer size and orbit far better than the planet's actual climate. To know whether a world is stable or not, we need to know what that layer of gas is made of, what the pressure near the ground is like, how clouds form, and whether water still exists or has gradually been lost over time. A thick sky is not always a good sign. It can shield the surface from radiation, distribute heat, and help keep water from disappearing too quickly. But it can also press heavily down on the ground, hold heat for too long, and turn the climate into a system locked in a hot state. In that case, the rocky surface, hypothetical oceans, and any complex chemistry would all have to exist under a very different kind of pressure. Not because Kepler-452b has certainly followed that path, but because the current data is not enough to rule out that possibility. Kepler-452b stands between two very different outcomes. An atmosphere that is just right could help retain water, give complex chemistry time, and make the surface a place worth considering in the search for living environments. But if that balance shifts too far, the same amount of light could become a problem. The difference lies in details that are extremely difficult to measure from nearly 1,800 light-years away. How much gas is enough to protect water? How much heat is enough to sustain an ocean? How many heat-trapping components are too many? Those things do not yet have certain answers, but they determine the entire meaning of Kepler-452b in the story of life. If there is an ocean there, its fate does not lie only under the light of the star. It lies within the invisible layer of gas surrounding that entire world. If the atmosphere determines whether water can be retained, then water opens a deeper layer of questions. On Kepler-452b, oceans are still not something that has been seen. No image has shown seas stretching beneath the light of Kepler-452. No direct data has confirmed coastlines, water clouds, or rain. Everything still lies within the realm of models. But in a favorable enough scenario, if Kepler-452b has a rocky surface, a stable atmosphere, and has kept its water, the ocean would become the first place worth attention. Not because water creates a familiar scene, but because water allows molecules to move, collide, dissolve, combine again, and remain within environments that can last through time. A single chemical reaction does not create life, but an environment durable enough, rich enough in material, and energetic enough can give chemistry more chances to become complex. In a scenario with an ocean, shallow water regions could be especially important. There, light from the parent star, minerals from rock, heat from the surface, and wet-dry cycles, if they exist, could together create an environment that is always changing. Before thinking about large organisms, we need to return to a smaller question. Could there be a chemical stage stable enough for simple structures to self-organize? Coastlines, if they exist, would not only be boundaries between water and land. They could be transition zones where material is constantly stirred together. Waves, sediment, dissolved minerals, and light could create conditions that change over time. In an environment like that, absolute stability is not always the most important thing. Sometimes it is the repeated cycles themselves that give chemistry more chances. Water retreats and minerals become concentrated. water returns, and molecules are dispersed and recombined. Over long periods of time, those small cycles could become part of a larger story. But Kepler-452b also sets its own limits on all of these inferences. If gravity is strong, terrain is low, and pressure is high, shallow seas may not operate in the familiar way they do on Earth. If a thick atmosphere holds heat for too long, water could become part of the mechanism that makes the surface even hotter. If the layer of gas is too thin, water may not be able to remain on the surface for long enough. So the ocean in this story is not a confirmation. It is a possibility suspended between many conditions that all have to be true. Another direction still needs to be kept open. If the surface is unstable, water could exist in more protected places. Beneath ice, inside cracks in rock, near internal heat sources, chemistry could still continue in ways less dependent on the sky above. Those environments do not create a dazzling image for the imagination, but they fit the way science often begins its search. Not from large organisms, but from places that are small, dark, durable, and rich in energy. This makes Kepler-452b interesting in a more cautious way. If water exists, the important question is not only whether there are seas. The important question is where the water is, how long it lasts, what kind of rock it touches, what energy source it receives, and whether it passes through enough cycles for chemistry to become complex. A vast ocean that is still and poor in material may not create many opportunities. A smaller environment, but one that continuously exchanges heat, minerals, and energy could be more remarkable. So before imagining plants, animals, or a sky filled with clouds, Kepler-452b forces humanity back to the first step. If there was ever a path toward biology, it probably began very small, not with a clearly shaped organism, but with silent reactions in water, on rock, under pressure and heat. Over enough time, an inorganic world could begin to create structures capable of preserving information about themselves. After water, imagination can easily go much farther. A world with oceans, light, and stable chemistry always makes humanity want to fill it with motion. But with Kepler-452b, this step has to be taken more slowly than any part before it. At present, there is no trace showing that organisms exist there. No biosignature has been confirmed. No oxygen has been measured directly. There are no surface colors, no seasons, no clouds, and no data clear enough to speak of a true biosphere. All that can be done is to place biology inside the conditions that have already been assumed. If a living process ever began on Kepler-452b, it would not develop separately from the planet. It would be shaped by gravity, pressure, water, heat, light, and the chemical composition of the environment. Life does not simply appear and then stand outside the world that gave rise to it. It has to take energy from somewhere, exchange matter with the place it attaches to, repair itself through change, and preserve information long enough for the next generation to continue existing. In the early stages, simple life forms are always the possibility that must be considered first. Not because they are less interesting, but because that is the more realistic starting point in a scientific story. A membrane, a mechanism for exchanging energy, and a way to copy information are the first boundary between chemistry and biology. Before there can be any large body, there must be small structures durable enough not to be destroyed after each cycle of heat, pressure, or radiation. If water exists on the surface, transition zones could play an important role. Shallow water, cracks in rock, warm seafloors, or places where minerals come into contact with water could all provide surfaces for molecules to attach and react. On a planet with strong gravity, water could also become a less harsh environment for biological complexity. Buoyancy helps reduce the burden on the body. A hypothetical life form in water would not have to resist its full weight the way a body on land would. If biology ever left the water and moved into drier regions, the pressure of the environment would become more apparent. Tall, slender structures that consume a lot of energy to support themselves could face many limits. Lower, sturdier life forms with better weight distribution may make more sense in a strong gravitational field. But this is not something that has been observed. It is only a direction of physical inference when placing hypothetical life into a world heavier than Earth. The important thing is not to turn these inferences into certain images. We cannot say that Kepler-452b has low forests, sturdy organisms, or oceans filled with strange forms of life. Those images only have value when they help explain a principle. If biology ever appeared on a heavy, warm world with high pressure and an uncertain climate, that world would shape it from the molecular level to the form of the body. Life, if it exists, would not be a decorative layer placed on the surface. It would be the result of many limits acting together over a long period of time. For that reason, the question of organisms on Kepler-452b should not begin with what they might look like. The first question has to be smaller and harder. Is there any environment stable enough for chemistry to self-organize? Is there any energy source durable enough to sustain that process? Is there any place that can protect fragile structures from being destroyed too quickly? Only if those conditions ever existed together would biology have a chance to begin. And every larger image, from plants to animals, must still remain within the cautious realm of assumption. In the end, Kepler-452b still does not appear as a world that can be seen with the eye. No telescope has ever recorded its horizon. Its oceans, if they exist, have still left no direct trace. Clouds, seasons, coastlines, the color of the ground, and every detail that makes a planet feel alive still remain outside the reach of data. Everything began with the light of its parent star, with one very small dip in brightness, and then with models built to understand what may have passed in front of that source of light. The distance of nearly 1,800 light-years makes every answer slow and blurred. The light carrying information from that star system left long before it reached humanity's telescopes. What has been recorded is not a present landscape in any direct way. It is only a late trace, enough to infer the orbit, the estimated size, and a few background conditions. The things viewers want to know most still remain out of reach. No one knows what the surface of Kepler-452b looks like. No one knows whether there are seas there or only dry rock. No one knows whether the atmosphere, if it exists, is holding on to water or holding heat for too long. Its magnetic field, geological activity, and chemical cycles stretching across billions of years all remain missing pieces of the picture. It is those missing pieces that will decide whether Kepler-452b is only a fascinating data point, or whether it truly once had an environment where chemistry could move closer to biology. This is the boundary that makes Kepler-452b both compelling and difficult to grasp. This planet is distant enough that every piece of data becomes precious, but also too distant for imagination to easily stay behind the evidence. Add just one layer of clouds in the mind, and humanity can already see a sky. Add water, and a coastline can be imagined. Add time, and life can begin to enter the thought. But science has to stop where the data stops. That does not make the story less powerful. It makes the story more real. Kepler-452b is not a world that has opened itself before our eyes. It is a planet seen through distance, through faint light, through probability, and through measurements that are still not enough to close the answer. Every possibility about water, climate, or biology must stand behind the word if. For that reason, Kepler-452b does not close the question of life out there. It only keeps that question open, calmer, farther away, and harder to answer. Kepler-452b does not leave behind a neat answer. It leaves behind a boundary. On one side are the facts that make humanity hope. A star more familiar than many stranger systems, an orbit close to the rhythm of Earth, and a position where liquid water still has not been ruled out as a possibility. On the other side are the things that cannot yet be measured directly. Its true mass, surface gravity, atmosphere, pressure, oceans, magnetic field, climate history, and every biological sign, if any, ever existed. That very gap is what makes Kepler-452b memorable. This planet is not proof that another Earth exists out there, nor is it a denial of hope. It is a world close enough to the things humanity is searching for to keep curiosity alive, but still too far away to turn that hope into a conclusion. Kepler-452b may only be a large, heavy, silent planet with no surface suitable for life. But in another scenario, water, rock, atmosphere, and time may once have met for long enough for chemistry to go further. For now, the most certain thing is not the answer. The most certain thing is that we still do not know. Thank you for staying with Astrexo until the end of the journey. If the story of Kepler-452b made you look at Earth in a different way, hit like, share this video, and leave a comment about what you think a world needs in order to truly become habitable. Subscribe to Astrexo to continue joining me on the next journeys, where every small point of light in the sky may be a question we are not yet close enough to answer.